dealing with today. So our first example here is going to use a table of values to figure out how to write a geometric sequence. And so for this first one, it says, is the sequence shown in the table a geometric sequence? If so, write a recursive definition for the sequence. Now, you might not know what a recursive definition is, so I went ahead and left a lot of the stuff in here. A geometric sequence, first of all, here's a definition. Geometric sequence is a sequence with a constant ratio between consecutive terms. This ratio is called the common ratio, which is R, otherwise known as growth factor. So in a geometric sequence, what we've been calling that previously in an exponential function is the growth factor. So for example, the common ratio for the plan A would be 2. The R value would be 2 because the common ratio is 2, which is the same as the growth factor. Over here, the common ratio is 3 because the growth factor is 3. So that's the same idea that we're looking at over here. We're looking at the Y values, by the way. So we got X values here, Y values here, if that's how you want to think about it. So to get from 4 to 12, what do you have to do? Multiply by 3. And we know we're multiplying here because that's the only way that exponential functions work, is by using multiplication of a common base value. That common base value is the common ratio, which is the growth factor. 12 to 36. Multiply by 3. Now, in order for this to actually be a geometric sequence, because it's asking us, is it a geometric sequence? In order for it to be a geometric sequence, we must have a common ratio. So as long as we're multiplying by the same factor, the same value every time, that gives us a common ratio, which makes it a geometric sequence. So times 3 times 3. It's all multiplied by 3. So everything is 3 times the previous. So the common ratio is 3. The sequence is a geometric sequence since each term is equal to the previous term multiplied by 3. So far, so good? This is all about multiplication. There's this other thing called arithmetic sequence. I don't know if you've dealt with those before, but those are not common ratios. Those are common differences, which end up being linear. So an arithmetic sequence basically makes a line on a graph. What we're dealing with, a geometric sequence, creates an exponential graph, which is why it's within the unit that way. So right here, a recursive definition for the sequence is, move on here. Actually, we'll head down here for a second. This is how the recursive sequence looks, first of all. So A sub n is equal to basically the value of y, whatever the term is. That's what A sub n is. So what we're going to do is we're going to start with A sub 1. What do you suppose that's going to reference? The first y value, yeah. N is the term number over here. So A is the term number, and then A is the term, N is the term number. So if you're talking about A, which is 4, with the first term number, the first term is 4. So A sub 1 is 4. So with our recursive definition, we're going to write this. So head back up here. We're going to say equals. We're going to write AN, or A sub n, any number in this sequence, any term in this sequence can be found with our beginning value of A sub 1, which is 4, the first term in the sequence. So first term. And then we put a comma, and there's a little bit of a space. And the first term, if we look at the table, the first term has an n value of what? 1. Yeah, n is 1. The first term has an n value of 1. The term itself is 4, so we just say n equals 1. So this first line always references basically the y value of the first term in the table and the x value of the first term in the table. That's essentially what we're looking at. And then down below, we are going to use our value of R. What's our value of R? 3. Yeah, R equals 3. So that's R. Oops. This is R, a common ratio. And so any term we want, we're going to take 3. And we're going to multiply that by the previous term. A with a sub n minus 1 means 3 times the previous term. And your value of n has to be greater than 1. So what this is saying is, if we want, let's say, the 5th term in the sequence, you would multiply 3 by the term that is 1 less than the 5th term of the sequence, which is the 4th term in the sequence, right? So if you want the 5th term, you multiply 3 by the 4th term. So here's the 5th term. If you multiply the 4th term by the common ratio, which is 3, that gives you that one. That's all it's saying. So it's a weird way of writing it, but that's all it means. You write your first term of the sequence with an n value of 1, and any number in that sequence you want, you multiply the previous term by 3. So the way to write a recursive sequence is right here. So let's just go ahead and write in some things. AN is, let's just say this is the nth term in the sequence. The nth term in the sequence, or the desired term in the sequence. Which term do you want? You want the first? Do you want the second? Do you want the 125th? Well, if you do, you need to know the first term of the sequence, a sub 1. So a sub 1 is the first term. N is the term number. And R is the common ratio. So that's where we're starting on. So the part B is asking us, is this one a geometric sequence? If so, write the recursive definition for the sequence. So the first thing you need to do is find the ratio between the terms. And our terms that we are given are 12, 9.6, 7.68, and 6.144. So these terms are decreasing, which means if we have a common ratio, that ratio will be what kind of a number? Yeah, it'll be a fraction or a decimal, right? It's going to be less than 1, essentially. It'll still be greater than 0, but it'll be less than 1 because it's not growing, it's decreasing. So that's like there'll be like a decay factor, right? So this particular growth ratio, or common ratio, I shouldn't call it growth ratio, a common ratio here is more like a decay factor than a growth factor because the numbers are getting smaller. And so if you divide every single one here, because they're decreasing, so we're not going to multiply, we're going to divide. If they're increasing, you try to figure out what you can, well, you can actually, you know what, you divide anyway. 12 divided by 4 is 3, 36 divided by 12 is 3. So division works either way. This one makes a lot more sense to use division though, because you're not going to figure out what multiplies by 9.6 to equal 12. Not off the top of your head. So division is probably a good way to go about doing this. 12 divided by 9.6 is 0.8. 9.6 divided by 7.6 or 7.68 divided by 9.6 is 0.8. 6.144 divided by 7.68 is 0.8. So do we have a common ratio here? Yeah, what is it? 0.8. All right, here we go. R equals 0.8. Let's fill in the things that we should be able to know here. And by the way, there are 2 things we should be able to know. We should know R and we should know a sub 1. What's the first term? 12. So if we are writing ourselves a recursive definition, we're going to write a sub n, any term we want, the nth term is equal to, get our brace there. Our first term goes up here, so we're going to write 12, comma, and that's the first term, so we write n equals 1. And the bottom row is going to be the common ratio, 0.8. And that gets multiplied by the previous term, which is a sub n minus 1, for all n values that are greater than 1. Any questions about that? This is very much a formula that we're plugging into, right? There's just spots where you take the thing from the sequence and you just plug it in. So a lot of what we're doing today is just like, I'm going to be giving you a few different formulas, essentially. This is the first one, and it's plugging it in. All right, work on A and B real quick. So it's always the next term divided by the previous term to figure out your common ratio. Just to make that clear. Hopefully A is a very quick one to do. What's the common ratio for B? Yeah, negative 0.5. Cool. And the first term is negative 1.5. So the recursive definition then, what's it going to be? How do we start it? What goes before the braces? Yeah, a sub n. So whatever term we're looking for, any term we want, the nth term, the desired term. And then we're going with our braces, top row. Okay, comma. N equals 1. Okay, bottom row. Negative 0.5. Yep. A sub n minus 1, comma, n is greater than 1. Cool. All right, any questions here? So you just take that, plug it in. By the way, your test for this chapter is going to be on Friday. You will be allowed to make your own page of notes for it. I would certainly include any formulas that would be useful. I would certainly recommend this one to put in there because that's a weird one in terms of as formulas go. And just remembering the exact details of it. It's not hard to use. It's just going to be hard to remember exactly the details. So questions before we continue? Cool. All right. Like I said, this is not going to be the most complicated lesson today. There's just a lot of different little formulas that we plug into. All right, this time we're going to flip it around. We are going to go between a recursive and an explicit definition. So the explicit definition is like what we did on the front page, where we had the first term multiplied by the growth factor, and that was to the x minus 1. Same thing here. So the formula that we have I'm actually just going to write it. Yeah, I'll write it up here. So the explicit definition is going to be a sub n equals, what do we call the first term? A sub 1. And then what goes in the parentheses? R, yep, that's our growth factor. And then x minus 1, but our term number is called here, we'll use n instead. But yeah, that's it. So we're using the same things that we did with the recursive. We're just writing it as a more formal formula that we've seen before. And by the way, this is an exponential function, right? We got our first initial value, growth factor or decay factor, and then exponent. So same idea. And so what we're going to do is we're going to plug in. And so what it says here, if we look at this recursive definition, we can see we have a first term of 5 when n equals 1. So that's our first term. Our common ratio is 1/2. So that means that every term is half the value of the previous term. That's what we're dealing with. And so if we just wanted to rewrite this, it tells you right here, the recursive definition is a sub n equals 1/2 a to the n minus 1. But that's the previous term. So if we multiply each one by the previous term, that gets us where we're going. So what we need to work on here is just take the first one, so the pattern. So if we take a look at a pattern here, by the way, let's just go with our pattern real quick. A sub 1. A sub 1 equals 5. Right? That's the first term. What's a sub 2 going to equal? 2.5. Yeah. Or half of 5, right? 5 halves. 5 times 1/2, whatever you want to call it. 2.5, 5 halves, 2.5. A sub 3. Yeah, and that would be the same thing though as the previous answer multiplied by 1/2, right? So that would be the previous answer of 5 times 1/2 multiplied again by 1/2. Which is the same thing as 5 times 1/4 or 5 times 1/2 squared. A sub 4 is the previous answer, 5 times 1/2 squared times 1/2, which ends up equaling what? What's 1/2 squared times 1/2? What's our new exponent here? 1/2 squared times 1/2 would be 1/2 cubed. All right. A sub 5. We're just generating a pattern so I can kind of show you exactly why this formula works, by the way. Equals 5 times the previous answer, 1/2 cubed times 1/2, which gives us 5 to the 5 times 1/2 to what power? The 4th power. Now, take a look. What is the relationship between the exponents and the term number? It's always what? It's 1 less. That's the n minus 1. Take a look. Hey guys, I want you to understand why this works. So this is one of the things that should make pretty decent sense, because if we start here, 5 times 1/2, that would be 1/2 to the 1st power, which is exponent is equal to 1 less than the term number. Right here, exponent is squared. So we've got our first term multiplied by the common ratio to a value of n minus 1. 3 minus 1 is 2. Same thing here. First term multiplied by the common ratio. Exponent is equal to the nth term minus 1. 4 minus 1 is 3. And so that's why we get first term times the common ratio to the n minus 1. It's exactly why this works. If we wanted to, we could put 1/2 in parentheses here with an exponent of 0, because 1 minus 1 is 0. So that's it. So our explicit definition for the sequence is going to be a sub n equals 5 to the 1/2, or 5 times 1/2 to the n minus 1. And once again, the general explicit definition for any geometric sequence is what we wrote up here. It's that same thing. So that's just any term is equal to the first term times, I shouldn't write 5. Any term is equal to the first term, a sub 1, times the common ratio to the n minus 1. So it's just the same thing we wrote at the top. And so again, this is just plug and play, right? The last thing we're going to do here is we're going to practice writing recursive one more time, because now that we actually have the explicit definition, we're going to go ahead and rewrite that using the recursive definition. Then we'll move on and maybe do a little bit of math as well. Because I haven't really done much in terms of math yet today. Done a little bit of division, but that's about it. Mostly just writing into a formula. So here we go. A sub n equals, here we go, braces. What goes on the top row? Three, comma, n equals 1. Bottom row. To a sub n minus 1, comma, n is greater than 1. Cool. All right. So transitioning between explicit and recursive. Now the difference here is recursive means you need to know the previous term in order to get the next term. That's what recursive means. Because if I were to tell you to find the 12th term of this particular sequence, you have to know the 11th term to find the 12th. You know what I mean? That has to be true. Here, if I told you to find the 12th term, you just plug in 12 for n and solve. So the explicit definition, in terms of how I'm seeing it, is more useful than the recursive one in general, because recursive means you have to know the previous one in order to get to the next one. So, all right, 2a down here and 2b. I want you to do both of those. So rewrite this one as explicit, rewrite that one as recursive. So just switch between the two types of equations that we have so far, definitions, I guess, as we're calling them. All right, here we are. Now, the reason why I'm calling that one S sub n is because it uses S sub n over here. That's the only reason for that. S for sequence. I think. I don't know. Maybe it just is S because it's S. In my mind, I'm saying it's S for sequence. All right. Any questions about the answers for A or B? Cool. So, I mean, like literally all it is just plugging in for the spots that needs to go. Substitution is it. All right. Like I said, lots of plug and play. Which sometimes is kind of nice. It reduces the amount of thinking you actually have to do, which on some days it's kind of nice to not have to think so hard sometimes. Doesn't mean it's going to stay that way in this lesson, but kind of how it is for now. Anybody need more time or have any questions before we move on? Cool, turn the page. All right, now you actually get to use it in some kind of a context. So a phone tree is when a person calls a certain number of people, then those people each call the same number of people and so on. So sometimes if you work for a company or something like that, and does anybody have that kind of thing going on with where they work? Are there phone trees where people work? Like if your manager calls you, you're then responsible for calling the next three people on the list, and then they're responsible for calling the next three people after that each. No, it's a thing. Even if you've never had it before, it's a thing. So it says in the fifth round of calls, 243 people were called. So that was round 5. 243 people were called. Write an explicit definition to find the number of people called in each round. So, does anybody have any thoughts on what we might be able to do for this particular problem? So, actually, let's go ahead and let's back up a little bit here. How many people were called in the first round? According to the chart. 3. Yeah. So A sub 1 here, let's figure out some numbers. A sub 1 equals 3. In the 5th round, A sub 5, how many people were called? 243. So if we're going to be writing an explicit formula, what information do we need? Because our explicit formula says A sub n is equal to A sub 1 times r to the n minus 1 power. What are we missing from this formula right now? What do we not know yet? Yeah, we don't know at all. We need r, we need the common ratio. And we have every other part with these two things to plug in order to solve for r. So let's use A sub 5 as our like demo value to figure out what r is. So if we plug in 243 equals, A sub 1 isn't going to change, that's always 3. And that'll be times r to the, what term is this? So what's our exponent? 4. Because A sub 5 is 243. If n is 5, n minus 1 on the exponent is 4. You could. But if it's a problem where it's kind of obvious like this one, yeah, that works. But oftentimes it's not going to be quite so straightforward. And so it'll be good to know how to do this using algebra versus just doing the division every single time. But yeah, that does work for it. And so if we divide both sides by 3, what do we get? What's 243 divided by 3? 81. 81 equals r to the 4th power. So we're looking for the 4th root of 81. What multiplied by itself 4 times equals 81? 3. Common ratio is 3. All right, so that means we have ourselves A sub n equals 3 times 3 to the n minus 1. So the number of people called in each round. A sub 1 equals 3. A sub 2, what does it equal? 9. A sub 3. A sub 4, 81. And A sub 5, 243. So that's what we have. Now from here, we want to know how many people were called in the 8th round of the phone tree. That's a big company, if it's a company. In the 8th round. So we're trying to figure out A sub what? 8. equals 3 times 3 to the 8 minus 1. Or 3 to the 7th power. All right. Yes. In this problem, that does work because A sub 1 is equal to R. If that is the case, then yes. What does it equal? Yes. People. There it is. Kind of easy, right? I hate using that word in math, easy, but not too bad. Okay, let's keep going. Number 3, a geometric sequence can be used to describe the growth of bacteria in an experiment, which means that bacteria in this particular experiment is growing at an exponential growth rate. On the first day of the experiment, there were 9 bacteria in the petri dish. What is A sub 1? 9. All right. On the 10th day, there are 3 to the 20th bacteria in the dish. So A sub 10 equals 3 to the power of 20. How many bacteria were there on the 7th day? I want you to work that out. Yeah. Yeah. So there's definitely a kind of difficult way to do this and a kind of an easier way to do this one. So if we take a look here, we're looking at 3 to the 20th power equals 9 times R to the 9th. Everybody got that so far? What do we do next? To solve for R, what do we have to do? I wouldn't do anything with the root yet. Because we want to get the R to the 9th by itself. Divide by 9. Okay. Now on this side, I'm going to write divided by 9. However, on this side, I'm going to divide by 3 squared. So those are going to cancel. 3 squared is 9, right? Now the reason why I'm doing this is because if you have 2 powers that have the same base, what can you do with the exponents when they're being divided? What was it? You can subtract it. Yeah. Exponents subtract here. So we don't actually have to multiply anything out to figure out what that big giant number is. We can just say 20 minus 2 is 18. And say 3 to the power of 18 is equal to R to the power of 9. Not only that, if we think back to rational exponents, because we have to take the 9th root of each side, right? Which sounds kind of gnarly. But a 9th root, if we think back to rational exponents, would be multiplying each of our exponents by 1/9. Everybody remember that from a few chapters ago? Square rooting is an exponent of 1/2. Cube rooting is an exponent of 1/3. Therefore, 9th rooting is an exponent of 1/9. So here, that cancels out. We're left with r. Over here, this is 18 divided by 9. What's 18 divided by 9? 2. R equals 3 squared, which equals 9. R is 9. And I didn't even have to touch my calculator to do that, because I kept everything in exponential form and just dealt with exponents and rational exponents. And I don't know about you, but I'd much rather keep things in exponential form than try to multiply out 3 to the 18th power or 3 to the 20th power for that matter. That's ridiculous. So remembering those things that we've done in previous chapters can actually really, really speed up and make this process a lot more efficient. So r equals 9, which means we have an explicit definition that can be written as a sub n equals the first term, which is 9, times r, which is 9 to the n minus 1. So how many bacteria were on the dish, in the dish on the 7th day? So what exponent are we going to have over here if we're on day 7? 6. We've got a sub 6 equals and I'm just going to do what I did on the solving for r. I'm going to write 9 as 3 squared here. I'm going to put parentheses and write 9 as 3 squared there to the power of 6. I'm just going to keep everything in base 3. Because then all we have to do is use exponent rules to figure out the answer as opposed to giant numbers. So if we multiply 3 times 2, or not 3 times 2, 2 times 6, we get 12. So a to the 6th power. No, that's not a to the 6th, a to the 7th, sorry. Not a to the 7th power, a sub 7. A sub 7 equals 3 squared times 3 to the 12th. And then to combine those two, we just add the exponents. And so a sub 7 is going to equal 3 to the 14th power. That's how many bacteria were there on day 7. 3 to the power 14. And we didn't have to deal with any long numbers written out because we just kept things in base 3 the whole time. Not to say that doing it the other way is wrong. I just think it would take a lot more time and it would cause a lot more writing because you'd be writing out really long numbers. Yeah. You could, as long as you combined those two together and made it like 9 squared or 3 to the power of 4. Yeah, that's fine. Wait, 7 here? Yeah, that's what I did. And that gave you a power exponent of 6. Because you got to subtract it. I thought you were asking, could you just start with 9 to the power of 7 to begin with? And the answer is yes, you can. Because 9 to the power of 7 is 3 to the power of 14. So if your answer was 9 to the power of 7, that's also correct. So if you wrote 9 to the 7th power as your answer, that works too, because it's the same number. Because that is equal to 3 squared to the 7th power, which would be 3 to the 14th. So either way. All right. Any other questions before we go to the next page? Cool, we're cruising. All right. Next. So that was geometric sequences. The difference between a geometric sequence and a geometric series is a geometric sequence allows you to figure out an individual number within a sequence. What term are we looking for? A geometric series, on the other hand, gives you the sum of all the terms in the sequence. So if you take all of the terms in the sequence that you want and you add them together, that is a geometric sequence. So as you can imagine, the numbers for a series are going to be quite a lot larger than the numbers that we get for a sequence in general. Like if you're comparing apples to apples, series values are going to be larger than sequence values because sequences focus on one term in a sequence, whereas the series focuses on the sum of the terms in the sequence. So S sub n represents the sum of a geometric sequence with n amount of terms. So I want you to write this down. I'm going to show you how this is actually developed. And so think about how would that actually work? Like, think of a sequence that has like 400 terms in it. How in the world could you possibly find the sum of those without spending a lot of time determining each value of the sequence and then having to go back and add all 400 numbers together? That sounds exhausting. Like days worth of work, days worth of work. That's a lot. Thankfully, there are people who are a lot more clever and smart than myself who've developed ways to make this stuff a lot more efficient. So if you have a sequence, S sub n, write this down. And that sequence is equal to the sum of all the terms, okay? The first term is always a sub 1. The second term is going to be the first term times what? Yeah, the common ratio. The third term is going to be a sub 1 times what? R what? Squared. The fourth term will be a sub 1 times the common ratio cubed. And so on and so forth, right? It just keeps going until we get to our desired term of a sub 1 times r to the n minus 1, right? That was the term value in a sequence that we just talked about. But these are all the other ones added together. Everybody okay with that so far? That's what we're looking at this point. Now, whoever decided that this was the way to figure out the sum of a sequence is brilliant, because it's, in my mind, it's not a very, it's a very understandable thing. There's no way I would have been able to come up with something so I don't know. I find this to be simple and elegant, which is really nice about math. If we multiplied everything in this term by the common ratio again, that means we basically just take r and distribute it to everything else, right? Which would just increase each of these by every r value here would increase by a factor of 1. Does that make sense? So that's what we're going to do. So we're going to say r times s sub n, which means we're adding a factor of r to everything here. So that this first term would be a sub 1 times r. The second term would be a sub 1 times r squared. The third term would be a sub 1 times r cubed. And so on and so forth. And then we'd end up with the nth term as a sub 1 times r to the n minus 1. However, that last term in the sequence also gets multiplied by another factor of r, which adds a 1 to this one here, which means there's one more term to add. And if you add another factor of 1, another factor of r to the end, what do you end up with? A sub 1 to the times r to what? Add 1 to the exponent, what do you get? Just n, yeah, because negative 1 plus 1 cancels out, and you end up with n. Now, if you have the sequence that is multiplied with the original sequence, s sub n, this is where it gets a little bit weird, and you subtract r times s sub n. Think about what happens when we subtract here. Like, actually look at it like subtraction. Is this a common term with that one? Like, are those like terms, a sub 1 and a sub 1 r? Are those like terms? No, that one's multiplied by R, that one isn't. However, this one and that one are the same. And this one here and this one here are the same. And this one here and this one here are the same. And one more color. This last term and the second to last term here are also the same. So it doesn't matter how many terms you have in the sequence. If you subtract the two sequences, you are left with the first term of the first sequence and the last term of the second sequence. And they're being subtracted because this is subtracting that. So basically, these all cancel. And you're left with a sub 1 minus a sub 1 times r to the n power. Now let's think about some algebra for a second here. Do you notice any common factors on the left side here? Is there something we could divide out of the left side? S sub n, right? S sub n is the sum of the sequence. This sum of the sequence and that sum of the sequence can divide out. And if we do that, we end up with the sum of the sequence equal to, if we divide S sub n by S sub n, we get 1. And if we divide R by S sub n by S sub n, we get 1 minus R in parentheses, because we divided out S sub n, which is the sum of the entire sequence. That's this. Everybody tracking so far? Because we're trying to figure out what S sub n is, but we're trying to do it without having to add up every single thing. And over here, do you notice any common factors? A sub 1, the first term in the sequence. So if we divide out the first term in the sequence, we're going to get 1 minus r to the n power inside the parentheses there. Now, think about this for a second. We want to figure out the series. We want to know the sum of all the values in that sequence, which is S sub n. We're only one step away from getting this by itself. What do we have to do? Think about this equation. How do we get this by itself? Think basic algebra for a second. That gets the sequence, the sum of the sequence by itself, doesn't it? So a geometric series, the sum of a geometric sequence is equal to the first term multiplied by 1 minus the common ratio raised to the nth term number divided by 1 minus the common ratio. That is how we can find the sum of the geometric series without having to actually add up all the numbers in the sequence. And we did it by basically just matching up the sum with the sum multiplied by the common ratio, and then subtracting the two and isolating the series itself. If that didn't make sense, that's fine. I just wanted to show it to you. This is what we're actually going to use, though. It's a plug and chug thing. You plug in for what you need, and you can find the sum of the series. That's great. That's all we're doing. Now, there's another way to write a geometric series. Kind of like we had two ways of writing geometric sequences, we have two ways of writing geometric series. We have our basic formula here, and then we have this form here, which is known as sigma notation. Those two things represent the same thing. Just want to make that clear. There's some symbols in here that represent certain things that we'll talk about. But this is the same as that. This is not in generic form. This is the generic form. This is the same as that. There's no difference between them. It's just picking the parts of it that fit in from here to here. That's what we're talking about here. So this is sigma notation is usually written in a way to say like, hey, I want to find the sum of something. That's what that big symbol there is for. And then the 7 on top of it, the 7 on top of it is going to be the term. The K on the bottom represents the term with which we're beginning. This here is still the first term of the sequence, and this is still the common ratio. So basically what this is saying is, find the sum of the first 7 terms of this sequence. That's what that's saying. So, if you take a look at the generic form, n still means n. A1 still means A sub 1. R still means R. K equals 1 means we're starting from the first term of that series or that sequence. So let's go ahead and just talk about this for a second. If we want the first 7 terms here, we could plug it in. I do want to show you in expanded form how it works, and then we'll use the formula to actually solve it. So here we go. A sub 1. What is A sub 1 in this series? According to that. What's the first term? Let's go ahead and say it. First term in this series here. 3. It's the number outside the parentheses. Our common ratio, R, is equal to what? 2/3. So every number after 3 is equal to 2/3 of that. All right, so we're just dividing or multiplying by 2/3 each time, basically, right? So A sub 1 equals 3, which means that A sub 2 is equal to what? What's 2/3 of 3? 3 times 2/3, what do you get? I'll just write it here. 3 times 2/3. Anytime you multiply a fraction, if it's a whole number, multiply the whole number by the numerator and then reduce if you can. 3 times 2 is what? 6. 6 divided by 3 is 2. Thank you. All right. A sub 2 is 2. A sub 3 is equal to 2 times 2/3. 2 times 2 is 4. 4 divided by 3 is 4/3. A sub 4 is equal to 4/3 times 2/3. We're just multiplying everything by 2/3. 4 times 2 is 8. 3 times 3 is 9. That's 8/9. A sub 5 is equal to 8/9 times 2/3. 8 times 2 is 16. 9 times 3 is 27. 16/27. That doesn't reduce. The 6th term, A sub 6, is equal to 16/27 times 2/3. That's 32/81. That also does not reduce. And then the final 7th term of this series is going to be 32/81 times 2/3, which is going to be 66/243. No, 64, not 66. What am I talking about? 64 243. All right. Those are the values. So if you were to add 3 plus 2 plus 4/3 plus 8/9 plus 16/27 plus 32/81 plus 64 243, that would give you the value of the series, which seems really annoying, right? Thankfully, we have ourselves a formula that we can use. That's very nice. So let's just go ahead and rewrite. We're not actually going to add those up. It's fine. We don't need to worry about that. But what we are going to do is find the answer to this sum without actually adding up all those separate values. So we're going to rewrite 7 over the sigma with k equals 1 with the first term of 3, common ratio of 2/3 to the k minus 1. K basically represents n in this situation. No, it doesn't. K does not equal n. Well, I guess it kind of does in this situation. So k minus 1, that's our value of n. That's the number we're going to plug in there. So as the actual formula, this is going to equal the first term, 3, times 1 minus the common ratio of 2/3 to the times, that would be to the power of 7 over 1 minus 2/3. That's how that translates. A sub 1 is here, R is here and here, and then n goes here. And then all we have to do is just type in a fraction on our calculators and fill everything in. So here we go. 3 parentheses 1 minus parentheses again, another fraction, 2/3. Close that first set of parentheses, take that to the power of 7, scroll to the right, close the second one, put that over. This doesn't have to be in parentheses down here. 1 minus, open up another fraction, 2/3. And we get 2,059 240/3. So that's what we would get if we added all those 7 values together, a sub 1 through a sub 7. But we don't have to because we can just plug it into the calculator and have it do the work for us. Great. So this is going to equal 2,059 240/3. That's our answer. That's the sum. So we don't have to do all that, ever. We just did it for this first one just to show you how much time you're saving. All right. So let's go ahead and jump down here to number 4. We'll probably have to finish with this today, and we'll do 2 more examples tomorrow. So we got a decent amount of the way through this. This is awesome. Okay, I'll get your assignment today as well. So we're going to write this sum, write the expanded form for this one here. So here we go. For A, S sub n, what does it equal? Give me the expanded form. That's this right here. What do we write on the numerator? What's our a sub 1 value? What's the first term in the sequence? 1/2. Parentheses, 1 minus, what's the common ratio? 3. What is our value of n? 5 over. What should we write on the denominator? What would be an easier way of writing 1 minus r for this particular problem? How about 2? Yeah, 2 is good. Cool. So type it in, give me an answer. Oh, sorry, it'd be -2 on the denominator, wouldn't it? 1 minus 3 would be -2. So what's the answer? Anybody have it? Just change it to the opposite of what you had before. Was it 60.5? Yeah. 60.5. Or 121 halves, either way. But it's positive. That should be a -2 down there. All right, now, what do you think we need to do for B? We're going to write this in sigma notation and then figure out the sum. So for B, let's go ahead and get that going. Now we're going to start with the first term, so k equals 1. And then what's our first term? -2, okay. What do you suppose our 1/3? Yeah, that's our ratio. And then we can write k minus 1 here. So how many terms later are we going to be at 243 on the denominator? So 5 terms later, which means we have how many terms total? Because if this is the second term, that's the last term in the current sequence, which is the 6th term for what we're doing. Because every time it's going 1/3, 1/3, 1/3, 1/3. So that's what we get for that. So now we need to figure out the sum. And in order to figure out the sum, well, we're going to have to write it as a sum. This will be the last thing we do today. So let's go ahead and say equals. That'll be -2 times 1 minus 1/3 to the power of 6 over 1 minus 1/3. All right, here we go. -728 243 is our sum. Cool. Overall, how are we feeling? I mean, it's just a lot of plugging in. It'll take practice to like really kind of get it so you can like remember everything, but